talked about how to take derivatives of polynomial expressions, radical expressions, and others, and we've learned how to use the shortcut rule along with the limit definition of the derivative. In this section we'll be looking at trigonometric derivatives, but before we do that, there's two important trigonometric limits that we'll want to know. Now these two trigonometric limits you'll probably want to have committed to memory or have them on your note cards when you go to take your exam. The first one we've already established using the squeeze theorem, and it's the limit as x approaches 0 of sine x over x. And we know from our previous work using the squeeze theorem again that this is equal to 1. Now if you plugged the 0 directly in, you'd get 0 over 0, which is indeterminate, which means to do more work, and of course the more work that we did was the squeeze theorem to establish this. Either one of these trigonometric limits that we'll have here can also be established using a numerical approach where we create a table of values that get closer and closer together. A couple things to watch out for when we're working on handwritten homework and exams. Make sure you always put parentheses around the arguments of your trig function. We'll see why that's important with this particular limit. Here's the limit as x approaches 0 of cosine of x minus 1 all over x. Now for this one, it's a little bit confusing, and just to clarify, am I taking the cosine of x or am I taking the cosine of x minus 1? So this problem would be different than this problem. So I always have to be really careful about what is the argument of my trig function. And one of those things that I'll look for very specifically is that you always have parentheses around the arguments of your trig functions. This limit is equal to 0. Now we can establish this using the squeeze theorem. We can also use numerical methods and some other methods that are a little bit beyond the scope of this class right now to establish these. But these two trigonometric limits you will want to have memorized. Now we can use these trigonometric limits in several different ways. One way we could do these if we had arguments other than just x. So let's go ahead and look at an example and use an idea of substitution in order to apply these two limits that I've just learned. So let's look at the limit as x approaches 0 of the sine of 5x, let's say, all over x. Now this is very close to this memorized limit that I have up here. It's not quite there yet though. But if I could make a quick substitution, it would be exactly what I would want. So let's go ahead and substitute. And let's let u equal 5x. So if we let u equal 5x, what I'd have here is the limit as, instead of x approaches 0, let's say I could have 5x approaches 0 of the sine of 5x. And then if I could just make this a 5x down here, that would work. But I can't just arbitrarily divide by 5. I actually have to multiply by 5 as well. So basically what I did here is I multiplied and divided by 5. 5 over 5 is 1. Now the reason I can switch this from an x to a 5x, as we're approaching 0, 0 times x or 0 times 5x is just 0. So when I make this substitution to let u equal this value, I end up with the limit as u approaches 0 of the sine of u over u. Now I have all of this here except for this 5 I have to pop out front. Now the reason I have to pull that out front is it's left over after I use my u substitutions. So when I take this limit, this piece right here, this whole piece goes to 1 by using this limit as x approaches 0 sine x over x. So this equals 5 times 1 or 5. So that's my limit here. So what I did was a direct substitution, letting u equal 5x, and then I compensated to create the 5x in the denominator. I actually had to multiply by a 5 in the numerator as well. Let's go ahead and try a few more of these. Sometimes it can be a little bit tricky, but once you see a few they should go pretty simple. This one we'll go ahead and do a double substitution. Let's let the limit as x approaches 0 of, let's do the sine of 3x over the sine of 4x. Now if we, of course, always look at these and we think, okay, let's plug 0 directly in. So this would be the sine of 0 over the sine of 0, because 3 times 0 is 0, 4 times 0 is 0. The sine of 0 is 0, so I get 0 over 0, which is indeterminate. And of course, indeterminate means to do more work. And I should always plug directly in to establish this, because if I can get this to work right off the bat, then I don't have to do any of these special steps or these substitutions, and I can get an answer right away. And also, it's important that I know what my limit is. Is it undefined or is it indeterminate? Because some indeterminate forms have some rules that go along with them that allow me to solve. So I guess up here on this one, I'm going to go back and double check this just to be consistent. If I make my direct substitution, I have the sine of 5 times 0, which is 0 over 0. Sine of 0 is 0. 0 over 0 is indeterminate. And of course, indeterminate means to do more work. Now, the more work that I'm going to do this time, I could maybe try something like the squeeze theorem or something, but what we want to try is we want to try using one of these limits that we consistently depend on in order to help us find the limits of other more complicated trigonometric expressions. So again, the substitution that I'll use here is let u equal 5x, and then we compensate for missing values and work from there. Okay, so to jump back down to this one, since we were right in the middle of it, do more work. So we can look here and we can see that I could split this up into two different pieces if I wanted to. I could look at the limit as x approaches 0 of the sine of 3x all over the limit as x approaches 0 of the sine of 4x. Now as we look at this, remember the limit of a quotient is the quotient of the limits. This is a limit rule that we learned back at the beginning of the class. We've already determined that this was an indeterminate form, and I want to make this look like the sine of x over x, or the sine of u over u. So I can go ahead and use that fact for that trigonometric limit to help us out here. So let's look to see what we have going on. If this was just a 3x down here, this would work perfect. But if I multiply by 3x, or sorry, if I divide by 3x, I actually have to multiply by 3x as well. Same thing in the bottom. If this was a 4x, this would work perfect, but if I divide by 4x, I actually have to multiply by 4x to compensate. So really what we have happening here, if I want to rewrite this, we have the limit as x approaches 0, and I have this sine of 3x over 3x now. And if I want to, I could say not just as x approaches 0, but 3x approaches 0. And in the denominator, I have the limit as, we'll say 4x approaches 0, the sine of 4x over 4x. Now let's see what we have left over. In the numerator, I have this 3 left over that I can pop out front. In the denominator, I have this 4 left over that I can pop out front. And now you might say, well, what about these x's? Well, x's cancel. X divided by x is 1. So basically what I have then is for each of these pieces, this limit piece I can rewrite. Get my marker to work here. So I have the 3 out front. Then I have the limit as u approaches 0 of the sine of u over u. And that, of course, is if I let the substitution u equal 3x. And in my denominator, I have the substitution will let u equal 4x. And I'm left with 4 times the limit. You know, instead of u in the denominator, we probably better use a different variable because we don't want to use the same variable twice. Let's use w. We'll have w equal 4x, so we have w approaches 0 of the sine of w over w. Now we know for each of these pieces, from our theorem that we have memorized up top for our trigonometric limits, that limit of the sine of u over u, or the sine of w over w, as w or u approaches 0 is 1. So this whole piece goes to 1. This whole piece goes to 1 as well for the same reason, and I'm just left with 3/4. So there's a lot to do here for this problem. First thing I should always do is plug directly in, and if I plug directly in, I have to make sure that I get an indeterminate form, and of course that indeterminate form means to do more work, and then we kind of keep progressing from there. So when you're doing these problems, always plug in first. Make sure you get an indeterminate form, because if we got a number here like 7 or pi, we would be done. So we should always plug in to check first to see what's going on. Okay, let's go ahead and look at another trigonometric limit that we can use those shortcut limits for. Now sometimes they don't look recognizable, meaning it's an example that looks close to something that you might know from those two limits, but sometimes they take quite a bit of rewriting to get them to a point that you can actually find the limit. So for this next one, let's look at the limit as x approaches 0 of the tangent of 2x. Remember, always put parentheses around the arguments of your trig functions. It's something I'm specifically looking for in your handwritten homework and in your exams, because this clarifies that the tangent is of 2x and not just the 2 or just the x. So again, really important to clarify that. We always put parentheses around the arguments of our trig functions. So the first thing that I should do is I should plug directly in. So if I plug in, I get the tangent of 0. 2 times 0 is 0 over 0. Tangent of 0 is 0, so I get 0 over 0 is indeterminate, and indeterminate means to do more work. So the more work that we are going to do here is rewrite and apply one of those formulas from the beginning. So let's look at the limit as x approaches 0. Now let's think about tangent. Tangent is sine over cosine. So sine of 2x over the cosine of 2x, and this is all over x. Now let's think about this x as x over 1. Now remember, when you divide by a fraction, you multiply by the reciprocal. So this would be the sine of 2x cosine of 2x times this x over 1 would flip and become 1 over x. So this x over 1, I'm dividing by x over 1, which means multiplying by 1 over x. So I'm going to rewrite this so you see where that comes from. Whoops, I'm in all sorts of trouble here. Okay. So let's go ahead and keep rewriting. I'm trying to get this into a familiar form. So let's look at the limit as x approaches 0. And I see this sine of 2x over x times 1 over the cosine of 2x. So I took the sine of 2x over x, rewrote it as one piece, and then I have 1 over cosine of 2x for the second piece. Now remember, the limit of a product is the product of the limits, so I can rewrite these. Limit as x approaches 0 of the sine of 2x over x times the limit as x approaches 0 of 1 over the cosine of 2x. So on this first limit, this one's pretty straightforward. I let u equal 2x. And so to use this, I divide by 2, and I'll multiply by 2 out front. And of course now I take the limit as 2x approaches 0. Now this next piece, I can do a direct substitution. As x approaches 0, I get the cosine is 0 here, and the cosine is 0 is equal to 1. So this whole piece goes to 1 over 1, or 1, because the cosine of 0 is 1. So I just have this first piece that I'm working with now. So I have a 2 out front, and I have the limit as 2x approaches 0, but we know 2x is equal to u from our substitution. The sine of u over u. Now we know from our special shortcut limits that this piece goes to 1. Now over here I already have a 1, so I have 2 times 1 times 1 basically from up above, which of course is equal to 2. So that's what this limit is equal to. Now if we wanted to, I could have looked at this numerically and created a table. I could have also used some other techniques of simplification to try and find this limit as well. But rewriting and using those two special limits is one of the things that I can do. Now the reason we like to know those two special limits is we use those to establish our trigonometric identities. I should say trigonometric derivatives. We'll work with identities in a bit. So the two theorems that we used up above, we used to prove these trigonometric identities. Now we're not going to focus in on proving these, we're going to focus in on making sure that we have a list of these and we can apply them to find derivatives. Now derivatives have the same meaning they always have. Derivatives are the slope of the tangent line at any point that's defined along a curve. It's a rate of change, so none of those things have changed. So we're going to memorize these trig derivatives. They're very important to know. The derivative of the sine of x is equal to the cosine of x. Now when we get to know the chain rule a little bit, we're going to be able to have an argument other than just x. We'll be able to have like 3x or half x or something, but for now we're just going to have an x involved. The other important one to know is the derivative with respect to x of the cosine of x is equal to a negative sine of x. So these are the two big trig derivatives, but of course we'll want to know all of them. Now if you think about these geometrically, these formulas make sense because both of them are periodic functions, so we would expect the derivative to be periodic as well. And both sine and cosine, of course, are periodic. The other derivatives that we'll want to have memorized here are the derivative with respect to x of tangent of x is secant squared of x, and the derivative with respect to x of secant of x is secant x tangent x. Now one mistake people make quite a bit is they forget to put the x in here. They write just secant tangent and don't have the arguments, and you need to have the arguments involved. Now over here, because we did tangent, let's go ahead and do cotangent. The derivative of cotangent is negative cosecant squared of x, and the derivative with respect to x of cosecant of x is equal to negative cosecant x cotangent x. Now I kind of set these up in a particular way because everything on the left, my derivative is positive. Everything on the right, my derivative is negative. So when I take the derivative of a cosine, cotangent, cosecant, the derivative is negative. So something to keep in mind. Also keep in mind that sines and tangents go together. If you want to think about tangent as sine over cosine, and tangents and secants go together in calculus when we're talking about derivation and eventually integration as well. So a couple of things to remember here. Now you'll have your note card for the next exam that you could put these trig derivatives on. We'll want to put them on in a little bit different form than we have right now as soon as we learn the chain rule. But on your Unit 4 exam, you'll have to make sure you have these memorized by that point because you'll have a portion for the Unit 4 exam that is without note card and a portion that is with note card. So let's go ahead and try and use some of these trig functions and find some derivatives. Now along with these you can also use the product rule and the quotient rule, and we'll actually get it to some chain rules and stuff eventually, but not in this section. So for this example, let's go ahead and look at the derivative with respect to x. Let's go ahead and look at sine of x minus x times the cosine of x. So I'm trying to take the derivative of this entire expression. Well, this first piece is going to be pretty easy. Now the derivative of a sum or a difference is the sum or the difference of the derivatives. So I can split this up into two pieces. So the easy part is right here. The derivative of sine is cosine. So there's my first piece. Now I just need to remember to drag it along. Now I'm going to put up my parentheses here because this is a product rule. I have two things multiplied together, so I'm going to use the product rule. Well, just as a quick reminder, product rule, and you'll want to make sure you have this memorized as well. The derivative with respect to x, f of x times g of x is our product rule. That was the first times the derivative of the second plus the second times the derivative of the first. So in this case my first is x and my second is g of x. So I'll write out the steps before we actually find the derivative. So first function, x, second function would be the derivative of the second function, the derivative of the cosine of x, plus the second function times the derivative of the first function. So that's the derivative with respect to x of x. So I haven't actually taken the derivative yet of that piece, only written out the plan. So these are y primes. I don't want to drop my derivative to say that this is my derivative. So an important thing to be able to do here would be, of course, to distribute the negative eventually. So x I just drag along. Now the derivative of cosine is a negative sign, so I need to have that in parentheses because I need to make sure I'm not subtracting but multiplying. Then I have the cosine, and the derivative of x is 1. So we have some cleaning up to do here. So y prime equals, I have the cosine x that I bring straight down. So here I have a negative x times a negative sine of x would be a plus x sine of x. And then I have a negative that I'll distribute over here as well as negative cosine of x. Well, I'm done, but there's some simplification that I can do. Cosine x minus cosine x is 0. So I'm left with y prime is equal to x times the sine of x. And please, one more time, always put parentheses around the arguments of your trig functions to clarify what's going on with those. Now, a lot of times in my math lab in your textbook it won't do that, but I think it's a really good habit to get into to make sure that you don't make mistakes a little bit later on. So if you get into that habit now, it'll help you out later. So that was an example of where we use the product rule, and we had a little bit of a sum here as well. Let's go ahead and look at another example. Let's go ahead and bring up the quotient rule for this one. So for this one, let's go ahead and look at my function is y equal, let's do 1 plus sine of x all over 1 minus sine of x. So this is definitely a quotient rule. So if we want to take the derivative with respect to x of f of x over g of x, that would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now in our case, the top is f of x and the bottom is g of x. So when you're working, it's always a good idea to write out the quotient rule just to serve as a reminder and kind of a pattern to follow. So for us, y prime would be the bottom. Always put parentheses around the arguments of your trig function, times the derivative of the top. So I'm not going to actually take the derivative of the top, I'm just going to write out what my plan is here. Bottom times the derivative of the top minus the top times the derivative of the bottom. And of course this is all over the bottom squared. Now when we write the bottom squared, it's just not 1 minus sine squared of x, it's this quantity, it's 1 minus sine of x quantity squared. So next step, we'll go ahead and actually take the derivative. Don't drop your derivative notation. You don't want to just put equal, equal, equal. You want to put down what this is. This is y prime equal. So 1 minus sine of x. Now the derivative of 1 is 0. The derivative of sine is cosine. So again, the derivative of a constant is 0. The derivative of sine is cosine. So for my next piece, I just copy down that 1 plus sine of x. Now the derivative of 1 minus sine of x, the derivative of 1 is 0. The derivative of sine is cosine. And there was a negative sign out front to begin with, so I need to leave that simplified. And this is all over 1 minus sine of x, quantity squared. Now this is my derivative. It's not in a form that's easy to work with, however. So we want to be able to simplify this if possible. Let's see if it will simplify at all. So I'll take the cosine and distribute. So I'll have cosine of x times 1 is cosine of x minus sine x times cosine of x. Okay, now I'll have a negative cosine, and then I'll have times 1 times another negative. So that's going to give me a positive cosine of x. Now here I'll have a negative sine of x times a negative cosine of x will be a positive sine x cosine of x. And this is all over 1 minus sine of x quantity squared. And so I see something that's going to cancel here, and that's good. Negative sine cosine, positive sine cosine. So it looks like I'm left with cosine of x plus cosine of x. Would be 2 cosine of x all over 1 minus sine of x quantity squared. So this would be my derivative, and again the derivative is the slope of the tangent line at any point along the curve. So I could find the equation of a tangent line if I wanted to from this formula. So these are just a few examples of how we can find and use derivatives using our trig functions. Now we also have higher order derivatives that we can find, but we'll look at those in just a second. For our next example, let's go ahead and bring up some other trig functions. Let's find the derivative of the function y equal secant x times, let's do cosecant of x. Now sometimes you can rewrite these so they're easier to work with. So secant would be 1 over cosine, and cosecant would be 1 over sine. So if I wanted to, I could rewrite this as 1 over sine of x cosine of x. But I don't think this is any easier to work with, so I'm just going to stick with this form. But sometimes it's a good idea to rewrite in terms of sine and cosine because some things could cancel. So this is definitely a product. I have my first function times my second function. So I'm going to make sure I note that it's a product, and then I will apply the product rule. So if we wanted to, we could call these f of x and g of x. So again, definitely a product rule. So for my product rule, if I have the derivative with respect to x of f of x times g of x, that's my first, times the derivative of the second, plus the second, times the derivative of the first. So to get started, I'm not going to actually take the derivative, I'm just going to write out my plan for taking the derivative. So I have my first function times the derivative of the second, plus the second times the derivative of the first. So that's my plan for taking the derivative, and now let's go ahead and take that derivative. So my secant of x, I just copy down. Now the derivative of cosecant. Now remember, the derivative of cosine, cosecant, cotangent were all negative, so I need to make sure I have my bracket up here. The derivative of cosecant is negative cosecant x, cotangent of x. Now if I don't have these brackets here, it would look like subtraction. So it's multiplication, so you've got to have those brackets there. Plus cosecant of x, and then the derivative of secant of x would be secant of x, tangent of x. And there's my derivative. Now this is not a very usable form. If we wanted to take a second derivative of this, let's say, this would be really difficult to work with. So first of all, let's go ahead and rewrite this and see if we can simplify this at all. I have a negative sign out front, so I have negative secant of x, cosecant of x, cotangent of x, plus I have a cosecant of x, secant x, tangent x. Now I see that we have a cosecant that's common. I could factor that out if I wanted, but I don't see that it would really be beneficial. So I'm going to rewrite everything in terms of sine and cosines. Secant I'm going to leave the negative 1 up top. Secant is 1 over cosine. Cosecant is 1 over sine. And cotangent is cosine over sine. Cosecant is 1 over sine, so knowing these trigonometric ratios is important. Secant is 1 over cosine. And tangent is sine over cosine. Now don't drop the arguments. Even though I say tangent is sine of cosine, of course it's sine of x over cosine of x. So it looks like cosines cancel here to leave me with a 1. Sines cancel here to leave me with a 1 as well. Rewriting, it looks like I have a negative 1 over sine squared of x plus, looks like a positive 1 over cosine squared of x. But 1 over sine squared is cosecant squared, so this is a negative cosecant squared of x. And 1 over cosine, of course, is secant, so 1 over cosine squared is secant squared. So if we're looking at this simplification, usually we would want to write that positive leading coefficient, so I'd rather rewrite this as secant squared of x minus cosecant squared of x. Now this is something that I can work with in terms of taking another derivative or evaluating to find an equation of a tangent line. Okay, we said we're going to talk about some higher order derivatives, so let's go ahead and look at some higher order derivatives, which means first, second, third derivatives. Let's go ahead and start with something pretty straightforward. Let's go ahead and start with cosine. Well, the derivative of cosine is a negative sine. The derivative of a negative sine, I drag the negative along, the derivative of sine is cosine. The third derivative, drag the negative along, the derivative of cosine is a negative sine. So that third derivative simplifies to just sine of x. Okay, let's go ahead and do with that fourth derivative, and I'm going to go up to Roman numerals here. So the derivative of the sine is cosine, and you can see I'm right back where I started now, so I can see a pattern here. So if I wanted to find the fifth derivative, it's the same as the first derivative because I see that this pattern holds. Now this pattern is going to hold true for other trig functions as well, like sine and cosine, not so much the other ones. Let's look at another example. Okay, so for this example, we're going to look at some higher order derivatives, and we can see that these can get out of hand pretty quick. So let's go ahead and look at y equal, let's do a negative cosecant x cotangent x. Now this actually came from the derivative of cosecant is negative cosecant cotangent. So if you want to think about it, the parent function of this was, before I took the derivative, cosecant. Okay, this is a product rule, so I have my first function and my second function. So let's go ahead and note product rule. That would be f of x times g of x derivative. That's the first times the derivative of the second plus the second times the derivative of the first. So let's go ahead and do this problem following that template. So I have my first function times the derivative of the second, and I'm going to actually write out my steps, plus the second function times the derivative of the first. Now when I do the derivative of the first, it's a negative cosecant x, so I need to make sure I have that in parentheses. And these others could be like cotangent x here, but it's not a huge deal. Without parentheses, this would be incorrect because it would look like d dx minus cosecant x. Okay, so I have my minus cosecant x, I'm dragging along here. And then the derivative of cotangent is negative cosecant squared of x. So I'm not sure I would put those big brackets up there. And again, it's a matter of memorizing those. The derivative of cotangent is negative cosecant squared. I have the derivative of cotangent. And let's think about the derivative of negative cosecant. So I drag along the negative. The derivative of just cosecant is going to be a negative cosecant x cotangent x. And we have to make sure we have those parentheses there because I'm multiplying, not subtracting. I think we have quite a bit of cleaning up we can do here because we want to find another derivative, and I don't want to find the derivative in this particular form. So this would be, oops, still the first derivative, we're just simplifying. So negative times a negative is a positive. Cosecant times cosecant squared is cosecant cubed. Plus, let's see what we have here. Negative times a negative is a positive, so I have a positive cosecant x cotangent squared of x. So there's my first derivative. Now remember, as usual, the derivative is the slope of the tangent line at any defined point along a curve. You know, I was going to find the second derivative of this one, but it's really ugly and we don't know the chain rule yet, and the chain rule would make this a lot easier. So I think I'll save that for when we know the chain rule. Let's try a higher order derivative with another example. So for this example, we're going to find a derivative, and of course we want to find a higher order derivative. Let's go ahead and start with the basic trig function. So let's go ahead and start with y equal tangent of x. Y prime, we simply have memorized the derivative of tangent is secant squared of x. And when we want to find the second derivative, I might want to think about this first derivative as secant x times secant of x. Now we could use something called the chain rule if you've seen that before to make this a little simpler, but we don't know the chain rule yet, so we're going to have to just stick by the old brute force product rule here. Brute force product rule, f of x times g of x. And it's a good idea to write down what rule you're using. So I'm going to use the product rule here. So the derivative with respect to x of f of x times g of x is equal to f g prime plus g f prime. This is just a shortcut notation without using the functional f of x, g of x. It's just a shortcut to help us kind of shorten up this product rule a bit. So to get started with my product rule, I have my first function times the derivative of the second function. So that would be the derivative of secant of x plus the second function times the derivative of the first function. Now this looks familiar. It looks like the first and second terms are identical, just in a different order. So I have my secant of x. Now the derivative of secant, if you want to look back or if you already have it memorized, is secant x tangent x. Same thing will happen over here. The derivative of secant is secant of x tangent of x. So simplifying, I have secant squared of x times tangent of x. And I have another one of these, secant squared of x times tangent of x. And since I have two terms that are identical, I can add them together. I have 2 secant squared x tangent of x. Now secant is 1 over cosine, and tangent is sine over cosine, so if I wanted to, I could also rewrite this in another form. Tangent was sine over cosine, so this would be 2 sine of x. Secant squared is cosine squared. There's a cosine for the tangent, so this would be cosine cubed of x. So either one of these are the correct answers. This is in terms of secant tangents, but if I rewrite this, I could get this in terms of sines and cosines as well. I don't think there's really one that's better than the other. Since nothing canceled, I would think that this might be the better form to leave it in, because rewriting, you usually want something to cancel. But no big deal, they're equivalent expressions, and I can use either one to find the slope of the tangent line or the equation of the tangent line at any point along a graph, if I was looking at the second derivative. So speaking of that problem, let's end with that example where we're finding the equation of a tangent line. Now if we're finding an equation of a tangent line, we don't need the second derivative, we just need that first derivative. So let's go ahead and find the equation of the tangent line. To the function y equal, we could use a product or a quotient rule here, but I think I want to stick with something pretty straightforward. Let's do 1 plus 2 cosine of x. And let's do this at the point x equal pi over 6. We use radians exclusively in calculus, so make sure if you're using your calculator for any of this, you're in radian mode. If this question was on a test and this is a reasonable question for a test, of course you'd want to make sure you have your unit circle memorized. So in order to write the equation of a line, we need to know two things. We need to know the point and a slope. So let's go ahead and look at the point first. We know the x value is pi over 6. Now we need the y value. So y would equal 1 plus 2 cosine pi over 6. 1 plus 2 and the cosine of pi over 6 is square root of 3 over 2. 2's cancel, and this is 1 plus root 3. So my y value is 1 plus root 3. Not ideal. You know, usually we'd like to just have a single integer. Next thing we want to do is to go ahead and find my slope. The slope would be y prime evaluated at pi over 6. Well, let's go ahead and find y prime first. So the derivative of 1 is 0. I drag along the 2. The derivative of the cosine is a negative sign. So simplifying, of course I just have a 0 here. These are prime marks. I need to make sure they look more like prime marks. 0, of course, is 0. 2 times a negative sine x is a negative 2 sine x. Now I want to evaluate this at pi over 6. So y prime pi over 6, I'll call this. Negative 2 sine pi over 6. The sine of pi over 6 is 1/2. The 2's cancel, but I'm left with a negative 1. So my slope is negative 1. So to review, you need a point and a slope. My point was pi over 6, 1 plus root 3. My slope was negative 1. So let's go ahead and start with point slope form. This would be y minus y1, and I want to make sure that I subtract all of this. So this has to be in parentheses, equals negative 1 times x minus pi over 6. So this would be point slope form. And I think that it's probably pretty reasonable to think about leaving this in point slope form, because once I solve for y, my y-intercept is going to be this combination of pi over 6's and constants and radicals. So for this example, I think I'll just leave this in point slope form. As usual, if you have questions, please let me know. You can take a screenshot of your question and text it to me. You're also welcome to use Pearson Connect, and I will be sending out a text pretty soon about how to use my online office hours. So good luck.